Okay, we had just, in the previous recording, just derived the Fourier transform and stated what these sine and cosine transforms are, all summarized on this chart, which would be on a formula sheet. These all came from the Fourier integral, which in turn came from the Fourier series as a limiting case. One warning to those of you out there who might be taking this in a different course. Sometimes these signs up in the exponents are reversed. This is the Fourier transform, and this is the inverse Fourier transform. Sometimes the signs of the exponents are reversed in different textbooks. This is the way mathematicians do it. Electrical engineers do it the opposite way. I'll just keep it like this because it came from a mathematics book. But let's do a few quick examples of doing these different transforms. Let's find the Fourier transform of this guy. First, the Fourier transform. So it's a little f of x. Fourier transform is a big F of the variable alpha. Some text that could be omega, but here it's alpha. It means find the Fourier transform of that little f of x, which means this is what the Fourier transform is from the formula sheet. So f of x is just a constant 3, but only between -2 and 2. So we integrate from -2 to 2, that thing. And this is just an integral you can take without resorting to tables. I'm not going to go through that so much. So here's an answer, or here's the answer. But we want to go a little bit further. For one thing, we don't like complex or imaginary numbers in the denominator. And we also like to simplify if possible. If you get used to Euler's formula, you'll recognize this as it's almost a sine of 2 alpha if I just divide it by I2. So I'll pull out an I, multiply by 2 here, and multiply by 2 in the numerator, so from 3 to 6. Now this part here is just sine of 2 alpha. So here's the answer in simplified form. I can go one step further. Here's the answer. If I multiply top and bottom by 2, I'll have 12 over 2 alpha. This part here is the sinc of 2 alpha. And here's what the sinc means. I've never seen a sinc before because it comes up frequently in Fourier analysis and frequency analysis. So anyway, here's the answer to that. That's the Fourier transform. Now let's take its cosine transform. Here's what it means. So again, we only need to integrate from 0 to 2 of 3. And we get almost the same answer. We're off by a factor of 2. Fourier transform was exactly twice the cosine transform. And notice in this case, this is an even function. So it's not quite that the cosine and sine functions are Fourier transforms or even and odd functions. There's a factor of 2 difference here. Well, let's look at an odd example now. This is an odd example. Let's find its Fourier transform. Because it's 2 different things for positive and negative x, we've got to break up the integral. And this is integrals you can do without resorting to a table. AX type stuff. I'm not going to go through the integral evaluation. Here's an answer. We're almost there. Let's at least get it all over a common denominator, which simplifies to this. Get rid of the minus sign. Here's the answer. Notice this guy is all imaginary. Odd function, you get a purely imaginary answer for the Fourier transform. Now let's find its sine transform. By looking at the formula sheet, it meant evaluating this integral. I could use what I call the Laplace trick. You could use a table. Use its answer. It's real. And it is exactly not just twice the other one, but 2i times the Fourier integral. You have an odd function. You get this guy. Let's do one more thing. Here's a function that's neither even nor odd. Now let's find the Fourier transform of it. Just one thing for positive x, so we only need to integrate from 0 to infinity. We can add the exponents, and again, this is just a e to the ax type integral. We don't need a table. I won't go through this. Here's the answer. We do not like complex numbers in the denominator. We'll get rid of that by multiplying numerator and denominator by this denominator's complex conjugate. So we multiply top and bottom by a plus I alpha. When you carry that out, you get this. Still a complex answer, but at least it's not complex in the denominator. So this is the preferred form of the solution. And here's some properties. If your function is even, your Fourier transform will be all real. If it's odd, purely imaginary. If neither, it's going to be something complex. And the cosine and sine transforms are always real. They're just used differently. Just think of the sine and cosine transforms as their own transforms. Don't think of them as the Fourier transform for even and odd functions. They're just their own transform. And with that introduction to Fourier transforms and the cosine and sine transforms, the next step is we'll use them to solve partial differential equations. And that will be the last part of this whole course called In Math B. That next time.